Let's get started with today's class. So, in the previous class, we discussed about the semiconductor technology and then the impact of this semiconductor technology on the process architecture and then the performance of the cost of the processor. So, okay. And then I explained that the CPUs are the kind of digital chip. It is the product of the digital system. So the CPU is actually the product of the semiconductor industry. Which means the performance and then the characteristics of processor design is highly influenced by the semiconductor technology level. Which means, so I believe you frequently heard about some technology node. So technology node means that it's the width of the semiconductor poly. Actually, the channel length of the CMOS transistor. So if this channel length is very narrow, then we can make the better transistors. So which means that power consumption, so some characteristics of these processors like power consumption and then area cost and some other characteristics will be better if we use the advanced semiconductor technology. But making very smaller devices actually is very difficult. So actually, the manufacturing cost is increasing, and then recently the semiconductor technology is very critical for the nation's industry. It's same to the other nations such as US, China, and also Europe. So it's not easy to make ferro transistors, which means that it's not easy to make ferro CPUs with very advanced semiconductor technology. So, in order to understand some manufacturing cost and then running cost of the processors, actually we need to understand, briefly understand. So, I know, so it's not easy to understand some detailed properties or detailed characteristics of the semiconductor CMOS transistors. So it's not our major. But you need to briefly understand how CMOS transistor works and then what influence the characteristics of the CMOS transistors. Okay. And then the most critical cost of the CPU chip is power consumption. That is the running cost of our computer systems. Also, the power consumption of the CPU, the processor, occupies the large portion of the power consumption of the computer system. So, and then recently, the server computers has a very large size of memory. So, which means the power consumption in the memory device is also very large. So recently, the portion of this consumption by memory devices is very huge recently. So in this course, we focus on the process architecture. So we focus on the power consumption of the CPU or GPU processors. And then, as I explained, the power consumption of the processor can be categorized as the dynamic power and static power. And then, actually, you need to understand the definition of the dynamic power and the static power. So, actually, in the undergraduate course, we covered the dynamic power only. But recently, the static power is getting more critical. And then, as I explained, the static power concerns about the 40 to 50% of the processor power consumption. So that's why the static power is very critical recently. Also, as I explained, the power consumption by memory devices is increasing because so we are using the large memory devices also. So think like the DRAM, like dynamic random access memory. And then if you think about how DRAM works in our computer systems, then you may understand why the DRAM or some other memory devices consume much power recently. So actually, we are not electrical engineering student, but it's a basic of the power consumption. So what's the power? Oh, the P is I multiplied V. So actually V is the supply voltage, and then usually, so we use the fixed supply voltage level. So actually this I determines the power consumption of the digital circuits. But think like this. What is DRAM? DRAM looks like this. So actually it's a ground. So electric charges are stored in this capacitor, and then by data 0 or 1. And then, so that means, so we need sometimes the electric charge pass through this transistor for this direction, or so this electric charge also pass through this transistor for inverse direction. So if electric charge flows in the wire, then it consumes electric power. So that's why memory devices also consume very much power. Also, think like static power. What is the static power? So just understand like this. So transistor is a controlled switch, electrically controlled switch. So what is the switch? We can turn off switch. So we can turn off our devices with switch, or we can turn on our devices. So actually, so we can control on and off of this switch. It's like a facet, means a 수도꼭지. So we can close our facet, or we can open our facet, and then we can use some water using this facet. But if the facet is not entirely closed, then we can observe the water flows through our facet, and then that's same to the transistor. So we can control on and off with this CMOS transistor with this gate voltage level, but if CMOS transistor is not entirely closed, then electric current flows from VDD to the ground. So it consumes electric power. And then the recent device, the CMOS transistor size is very small, so which means that we cannot entirely close this circuit. So which means the electric charge passes through this transistor, even though this transistor is turned off. And then it's the same to the memory. So think like this DRAM. This is the CMOS transistor switch. Actually, not CMOS, it's an NMOS transistor switch. So we try to close this NMOS transistor with this water line, the voltage level, but the NMOS transistor is not entirely closed. So which means electric powers can be dissipated, or electric charges can be dissipated from this capacitor. So which means some very small current, but it's very small current, but the current is flows through this NMOS transistor. Which means DRAM. So memories are also highly influenced. Memory power consumption is also highly influenced by static power consumption. So recently, so actually traditionally we focus on the dynamic power only. So which means that, and then in the computer devices, what is the most dynamically operating components? It's processors. The memory device is actually very cool devices, which means that So actually the data is stored in the memory devices, but the data is not, so it's changed, but it's not changed as frequently as a processor. So in the processor, every data or every electric signal level is changed very frequently with the clock frequency, but the data in the memory is slightly changing. Actually the memory device is not dynamically, it's dynamically changed. So I said it's not frequently changing. So memory device is actually cool. And then if we just consider about the dynamic power, so dynamic power is not important, it's not critical for these memory devices. So if we just focus on the dynamic power of the computer systems, and then the power consumption by processors dominate the power consumption of the computer system. But it's not true today. So actually the static power is dominant. So that means we need to also focus on the power consumption by memory devices, also the processors, and any other components. So the trend is changing but why? The semiconductor technology. So actually the characteristics of these transistors are changing. So which means the technology trend is also changing. So we need to focus on some different aspect of power consumption in our and some other cost in the computer systems. So, and then sometimes we are confused between power and energy consumption. So actually the energy is the integrated power over time. So actually, if we just focus on the workload, and then we just if we just focus on some integrated consumed electric charge, then we need to consider energy. And so the energy is so I said the energy is the integrated power consumption over time, which means the energy focused on the amount of charge consumed by a computer system. So energy is actually, think like mobile devices. In the mobile devices, battery has the capacity of the battery is measured by the amount of electric charge actually. So if we just focus on the workload and then some amount of consumed energy, so amount of integrated power over time, then we need to focus on the energy, and then which is also very important. And then power. Power is the consumed electric charge during unit time. Okay, so power is also very critical for the processor design and chip design, because the power consumption decides the manufacturing cost, also the running cost. But the running cost is also highly related to the energy. So, but the power consumption is highly related to the manufacturing cost, because its power consumption level decides the package, the kind of packages, and then some cooling cost. It's a manufacturing cost, okay, right? So it's the cooling cost also determined by power consumption. But if we just focus on the integrated power by some workload, then we need to focus on the energy. So energy is the power multiplied by delta T. Okay. So I believe so actually the computer architecture is the interfaces between it's handling the interfaces between hardware and software. So we need to have some knowledge on hardware design. Also, we need some knowledge on software. So actually, we need a broad knowledge, but so shallow knowledge, but we need actually, as a computer architect, so we require very broad knowledge. Okay, so we need to understand how transistor works, and then what's the characteristics of the digital design, and then cost of the CPU design, blah blah blah. Also, we need to also focus on the performance of the software, influenced by some hardware design or some architecture or system software, and so on. So we need a very wide range of knowledge. Okay, and then, but the technology in the process of design, the technology is changing recently because we are facing the end of Moore's law. So the Moore's law means that as time, so we can use barrel transistors by years. So that is the definition of Moore's law, but the Moore's law is ending, so which means that we cannot use barrel transistors, but we need more powerful, so higher performance, which has higher performance. So we need more powerful processors. That's the demand from some workloads, software, and also those are demands from our real world. So how can we how can we improve the performance or some performance is the first factor of this process of design. So how can we improve the performance of our processor? So we can actually develop some new types of processor, such as the domain-specific architectures. Also, we can use some different technologies, such as the quantum computing or some nanotube technology or analog computing. But it's not easy, because think like the semiconductor technology. So actually, this CMOS technology is mature. So every chip device depends on this semiconductor technology. So we can develop the quantum computers or some new devices such as the carbon nanotube. We can develop the analog computing, but I don't think this is the available option. So usually the analog devices consume much more power than digital devices. But sometimes we can consider the analog processors, but I don't think this is possible if we just consider some running cost of the devices. So we can use the different devices such as quantum. Actually, the concept of the quantum computing it's very different from this digital design, because in the digital design we have only two values, 0 and 1, but the quantum computing, it's related to some modern physics. The state of this quantum bit chain is determined by some probabilities. So actually, in the digital devices, the result of a digital system, it has only two values, and then it's deterministic, so 0 and 1. But if you are interested in some modern physics, so we can know that the state of the material is determined with the probability. Actually, the quantum bit has some more than two states. So it's different. It's so different. Also, it's very different. So we can apply to some new devices like quantum carbon nanotube. So it can be possible, but it's not mature currently. So it will take time. So actually, focus on the semiconductor technology also. Okay, so in this time I will discuss about some transistor basics. So actually, the transistor means it means the NMOS or PMOS transistors. Actually, most transistors like BJT. Sometimes, if you are working on a very low level of the computer system, then we need to understand how transistor works, how some very basic devices work in our processors or memory devices. So as I mentioned, we require a very broad range of knowledge, but an entire level of the knowledge. So try to understand the transistor basics. So let's focus on the MOS transistor. So if we just, and then, the most of the processor design is so I mean, the processor is the kind of digital device, the digital system. So which means that these digital systems are implemented with the MOS transistors. And then, as I explained, you can understand the operation of the MOS transistor like electrically controlled switch. So it's a controlled switch. So which means, so there are actually three nodes in the MOS transistors. It's a gate, source, drain. So actually the current flows from source to drain. Okay. The source is, the source is some how can I say, some materials are generated material, like water or some materials is generated from source, and then also drain. So drain means like 배수구 in Korean. So which means that the material generated from source is consumed in drain. Okay. A MOS transistor has three ports like source, drain, and gate. So actually, electric charge flows from source to drain, and then these electric charge flows are controlled by gate. So that is the basic operation of the MOS transistor. And then by combining many of MOS transistors, we can build digital systems. So let's just focus on some operation of the MOS transistor in more detail. Okay, so you can understand the MOS transistor is the controllable switch, and then this the electric charge flows in the MOS transistors is controlled by gate voltage. Then how can we control this gate voltage? So which means we need to focus on this voltage level of the gate port, like V, G, S. And then based on this gate voltage level, the characteristics of MOS transistors are changed. Okay, so let's focus on. So actually, we already know that the MOS transistor is the kind of, it's called the semiconductor devices. So what's the semiconductor? The semiconductor. The conductor means that the electric charge can through these conductors, but semi means that it's a half conductors. So it's controllable. So how can you control these characteristics of the semiconductor material? So if we see, if we see that this MOS transistor, the MOS transistor has also source port and the drain port, and then actually this base material is called the substrate. Okay, and then this base material is doped with P material. So which means that this material has the more holes, which means you can understand the holes like a positive charge. Okay, positive charge. And then this source part and the drain part are doped with the N material. Okay, so N material means that this N material has more electrons. Okay, so which means the minus charge. So it's negative charge. So initially this P substrate has more holes, positive charges, and then its source and drain part has more negative charges. So actually the current cannot go through from source to drain. Okay. So how can we so how can the electric charge go through this channel? So if we have conductor material, so like the conductor material, what does it mean? What is the property of the conductor material? So if we use, so actually we learned this property from the high school, maybe high school physics. What is the property of the conductor material? So it means conductor material has many free electrons. Okay, so which means if there are many free electrons, then the electric charge can go through this conductor material. But think like this transistor. So we have source part and the drain part, but the electric charge cannot go through this from source part to the drain part because this P substrate does not have enough free electrons. Okay, because it has more holes, more positive charges. So if this gate voltage level is less than threshold voltage, so actually less than threshold voltage, then the channel is not generated. So let's start from the start point. So let's think like this. So actually, this is the base voltage, like ground, and then let us assume that the gate voltage is also 0 volt, which means the ground. So which means there is no difference in voltage level from between gate voltage to this body voltage. So which means the 0 volt. So that means this P substrate between this source and drain has many holes. So there is the amount of free electrons is lower. So if any of these holes, so channel is not generated. So I will also explain about the channel later. So think like this. There is no free electrons. Actually, so there are some electrons, free electrons, but so in this MOS transistor, there are more holes. So electric charge cannot go through from the source to drain. It's closed. Okay. Then so let us assume that this voltage level is increasing. Okay, so which means the VG is increasing. So which means the voltage level has some differences between VG and VB, or VG or VS. So if this voltage level is increases and it has the positive voltage, so which means the electrons in this P substrate is moved to the near gate port, okay, because this gate has higher voltage. So which means some very shallow channels is generated, and then this shallow channel has more electrons. So think like this. Oh, this voltage level is high, so electrons in this P substrate move to the near this gate port, the gate. So the channel is generating, and then if this VG gate voltage is higher than the threshold voltage, then channel is generated from between BS to BD here. Okay, so channel is generated like this. And then also, let us snap VDD is now ground. Okay, and then VS is connected to the high voltage like VDD. And then channel is generated. If channel is generated and then VDD has VS has the higher voltage than this drain part, then which means the electric charge can pass through from source to drain. Okay, so when which condition VG is higher than threshold voltage, and then if the VDD is VS is higher than VD, the drain voltage, then the electric charge can pass through from VS to source to drain. Okay. So which means the transistor is turned on. Okay. And then if electric charge moves from this source to VDD, and then actually the electric devices. So electric devices has the parasitic capacitors, and then these parasitic capacitors are filled with the electric charges, and VDD also has this drain part also. This level is increased. So if the VS is similar to the BD, like a drain voltage, then which means the parasitic capacitance in this CMOS transistor is filled with some electric charge, then the current does not flow from source to drain. Okay. So this is the basic operation of the MOS transistor. Okay. So actually, the MOS transistor has 3 different operation modes. So like the double threshold region is like a cutoff region, and then linear region, and then saturation region. So actually, these 3 conditions are determined by gate voltage, and then also the voltage level between the source B. Okay. VDS. Okay. DS. So what is the cutoff region? So this means that it's the turned off. The transistor is turned off. So which means the channel is not generated between drain, source and drain. So this cutoff region is defined as if the VGS, that means the gate voltage level is less than the threshold voltage, which actually this is very important in the most transistor technology. If then no current flows, that is the that is true for some traditional some actually old semiconductor devices, but it's not true now. But usually in the cutoff region, no current flows from source to drain, between source to drain, because the VGS is less than threshold voltage. And then linear region means that, so this is working. So the most transistor is working in the linear region and the saturation region. So in the linear region, the condition of the linear region is that the gate voltage level is higher than the threshold voltage. And then, this gate to DS, so which means this is the voltage level between the gate to source, and then the voltage level between source to drain, SDS, so SD over DS. So the VGS minus VDS is higher than the threshold voltage, then this is the linear region. So which means IDS. So the current flows from source between source to drain, and then this IDS is proportional to this level. Okay, so what is observed? So if you see that this IDS is proportional to beta multiplied by VGS minus threshold voltage and then VDS. So if we see that this linear region equation, we can find that this IDS. So why do I focus on IDS? Because it's related to power consumption actually. So IDS is proportional to the VGS minus the threshold voltage level and then VDS. Okay. So which means the transistor is turned on in this case in the linear region. Then so the electric charge can move through this limit the channel, the electric channel between the drain and source and drain in the linear region. And then saturation region. The saturation region, the VGS is also high, but the voltage level between VGS minus VDS is below the threshold voltage. Okay? So in this case, it's a saturation region. So which means in the saturation region, we can also observe some current, but this current is not proportional to the VDS. Okay, so which means if the VGS, so which means that the gate voltage is higher than this threshold voltage, then and then based on some VDS, so the voltage level, voltage difference between source and drain. So it is firstly is in the linear region and then it's saturated. Sometimes, yeah, so we can observe that this IDS, the current between source and drain are firstly proportional to the voltage difference between VDS, and then it's saturated. So actually the analog design exploit this region or this region. So actually if we just utilize this region, then we can make some amplifier, the analog devices using the CMOS transistor. And then the saturation region, the saturation region is not proportional to the VDS. Okay, so just some, actually it's proportional to the gate voltage level, but in the saturation level we cannot control this IDS using the VDS. Okay, so as a digital designer, we just focus on the BG. Okay, BG and threshold voltage. So it means if the VG, the gate voltage level is less than the threshold voltage, then it means that this transistor is turned off, so it's closed. And then if the VG is higher than the threshold voltage, then transistor is turned on. Actually, the designer used these characteristics of MOS transistor. But I explained that we need to focus on the VTH, just threshold voltage. So why? So if we see the linear region equation and then saturation region equation, then we can find that IDS, the current level between source and drain is influenced by VGS minus VTH. But you know, in the digital design, we just focus on the VG can be VDD or VG can be ground because it's a digital. So we just focus on the two levels, like 1 and 0. So, but why I am talking about the IDS? It's the current level. So which means the amount of electric charge go through this MOS transistor circuit. So which means if the IDS is high, IDS has the high value, the current level is high, which means more electric charge can pass through between the CMOS transistor circuit. So you know, actually the basic operation of the electric circuit is that, so current flows, and then this current fills the parasitic capacitors, and then if the parasitic capacitors, the electric charges are filled in the parasitic capacitor, then voltage level is changed, and then so this capacitor has the different voltage level, which means the different signal, different data. Okay, so this current level is high, which means that this capacitor can be filled very quickly, right? And then which means the circuit works very quickly. The state is changing very quickly, which means it works faster. So what does that mean? So actually the linear region is very short. So actually we focus on that. But if we can observe that the IDS is proportional to the VGS minus VTH. So which means if the VTH is low, then we can make fast device. And then if VTH is high, then we can make slow device. Oh, which means then we can say that, oh, then everyone knows fast devices. Or then we can reduce the voltage level, the threshold voltage, VTH. Then we can make the very fast devices. It was true. And then Actually, this threshold voltage level is determined by semiconductor node. So which means the channel length, channel width, channel length of the is most transistor. So which means if we can make smaller devices, that means the technology node is advanced. So channel length is shrinked. Then we can reduce the threshold voltage. So which means we can make the best device also. But there are many factors actually for the best device. But actually, because so if for the same technology node, this current level is determined by the threshold voltage. But why do I explain this? Actually, the static power. The static power is also influenced by threshold voltage. Okay. So currently, so actually the technology changes. So we need to focus on the different factors. So if the VG, the gate voltage level change very quickly, then actually we just focus on the on and off of the transistors. But the current between source and drain is influenced by this threshold voltage, and then this IDS is now. So IDS is very critical for the static power consumption. So the static power can be also controlled by VTH. Okay, the threshold voltage. So by adjusting the threshold voltage, then we can also change the characteristics or properties of most transistors. Then by changing this, then we can also change some slow devices or faster devices. And then some devices may consume very high static power, very low static, maybe static. We can also reduce the static power with the threshold voltage. Okay, so let's focus on the scaling technology scaling. So it's called the CMOS scaling. Okay, so this is some typical structure of the MOS transistor, and then the MOS transistor is composed of, as I explained, it's a p-type substrate. So it's a substrate, and then we can actually this is the NMOS transistor structure. So we just focus on the NMOS. And then if we see that this NMOS structure, NMOS has the p-type substrate, it's a base. Sometimes it's called base. And then over this p-type substrate, we dope the source part and then drain part with the n-type semiconductor. So it has different characteristics. And then this channel length. So actually the distance between source drain is called the channel length. Sometimes it's called the channel width, but in this textbook, we just call this the channel length. Okay, the channel distance or channel width or channel length, but just focus on that. So in this textbook, in this course, we just call this is the channel length, and then it's the L. Okay, and then if we just talk about the technology node, which means technology node means actually is channel length. So that means the 4 nanometer technology or 5 nanometer technology means that this channel length is actually 4 nanometer or 5 nanometer technology. Okay, it's very, very narrow recently. And then actually this most transistor is 3D material. Actually, everything is the 3D material because we live in the 3D world. So actually, if we just focus on the most transistor, it's just planetary devices actually. So this size, so also decides the size of the entire transistor. So actually this is called the channel width. So this also determines the width of the source part, the drain part, also the gate part. Okay. And then if we just focus on this gate, actually this gate structure is a little bit complex, of course. And so if we just focus on this gate part, so gate is it's connected to the metal layer. Okay, so what is metal? It's a conductor. Okay, it's a metal layer, and then under this metal layer, we can find the silicon dioxide. Actually, this silicon dioxide is the 부도체를 뭐라고 했더라? So that means that electric charge cannot go through this silicon dioxide. 뭐라고 했더라? 갑자기 까먹었네. Okay. So metal is the conductor. And then this silicon dioxide, so actually the current cannot go through this silicon dioxide. Okay. And then the thickness of this silicon dioxide is defined as the TOX. And then, you know, if we just think like the capacitor, actually, if we just about this capacitor, the capacitor is composed of two metal plates, and then between these two metal plates, the material between these two metal plates is the so that means that the electric charge cannot go through this material between these two metal plates. So it's the structure of the capacitor. 도대체 뭐로 보더라? Insulator, right. It's an insulator. Thank you. So silicon dioxide is the insulator. So actually, but this the voltage difference between the gate part and then the body part, the substrate part, can also influence some voltage level under this silicon dioxide. Okay. Then in this most transistors, we can also define the supply voltage and then threshold voltage also. The metal wires are connected to source, gate, and drain. So this wire width and height is also determined by these parameters. And then Moore's law, if we just talk about the Moore's law, then Moore's law means that these vectors are scaled down by S. That is called the Moore's law. Okay, so which means, and the Moore's law is applied. So Moore's law continues. So L becomes the L over S, and then the W becomes the channel width becomes the W over S. That is the Moore's law. And then by the Moore's law, the scaling factor is the square root of 2. So every 2 years. Okay, the S becomes the square root of 2. Then So we learned about this operation of the MOS transistor, and then if we just focus on some factors of this like some transistor gain or current, and then some other parameters in the MOS transistor, and then if the MOS transistor is scaled down, with the scaling factor S, and then we can also calculate these MOS transistor parameters, like characteristics. Okay, so transistor gain is called the beta here. You can find the transistor gain from this slide, like the beta here. So it is also influenced by these parameters. Okay, so if we just apply the scaling factor, then we can know that this transistor gain can be S. So which means that if we scale down the MOS transistor with S, so which means that these parameters becomes the 1 over S. So then beta becomes the S. Then the current is usually beta multiplied by VDD minus VTH. So which means IDS. IDS also becomes the S times of the old device. Okay. So and then I explained that if this current is increased, then we can also increase we can also build a faster device. Okay, it's faster. So the device can run faster, which means that we can increase the clock frequency. So which means we can make the CPU which have higher performance. And then actually the resistance is 1 because this is a supply voltage. So and then with this scaling factor, we can also reduce the supply voltage by 1 over S. And then the VDD is reduced by 1 over S, and then IDS is what is this? Resistance is IDS is the S. So S 1 over S squared. No, I don't think so. I don't know why. I need all this resistance. Okay, so if we just focus on the gate capacitance and then gate delay, it becomes the 1 over S and then 1 over S also. And then it's important, the clock frequency. So clock frequency becomes the S, because when we define the delay of the circuit, actually the delay of the circuit is defined by the 1 over RC. Okay, and then the gate delay is RC, and then it becomes the clock frequency can be S. And then circuit area. So the size of the single transistor is defined by this L and W. So channel length and then channel width. And then if this MOS transistor is scaled down, the circuit area becomes the 1 over S squared. Okay. Actually, if we just estimate the performance and then the clock the area cost with the scaling, then we just focus on this clock frequency and then circuit area. And then the clock, we can increase the clock frequency with the S, with the scaling factor. And then so this is the 2D device, the plenary device. So we can reduce the circuit area by 1 over S squared. And Y resistance is S squared, and then Y capacitance is 1. But this is the important factor, clock frequency and circuit area. So actually, this is a good thing. Why? So we can talk about the benefits of scaling. So which means we can make the if we can make the smaller devices, smaller transistors, then the benefit of scaling means that we can increase the clock frequency, and then we can also reduce the area occupied by a single transistor. So device density increases, and then also frequency so increased by 41% because it's defined by this scaling factor. Okay. And then let's focus on the power consumption. If we just focus on the dynamic power, that's the P dynamic. P dynamic alpha C P scale F. Okay. And then the benefit of scaling is that we can reduce the supply voltage by 1/s. And then C, capacitance is the actually is the same because the area is the same. So actually the C, this capacitance is proportional to the area of the circuit. Okay. It's the same, and then it's activity factor is the property of the software, but usually its activity factor is the constant, and then F, we can increase the F like S. So if we just focus on the dynamic power, then it's 1/s square, then S. Right? And then no. Okay. So capacitance is also reduced. We need to focus on also capacitance because we need to focus on this dynamic power of the single transistor. Okay. So the capacitance is also reduced. It's 1/s, and then it's 1/s square, and S. So this is the P dynamic power. Actually, with the simple estimation, the P dynamic power becomes the 1/s square. And then, this is the dynamic power of the single transistor because with the single transistor, this gate capacitance is reduced. Okay, so I just talk about the dynamic power of the single transistor. So, and then with this scaling, with this CMOS scaling, so we can know that the size of a single transistor is reduced by 1/s square. So which means in the same area, we can include the S square transistors. Okay. So the number of transistors, it becomes the S square, and then the dynamic power is the 1/s square multiplied H constant. So what is the benefit of scaling? Power density. Power density by area is the constant, but we can make the better device, better processor, because we can increase the F, okay, clock frequency. So without doing any architectural effort, without doing some architectural ideas or solutions, if the semiconductor technology is advanced, then we can use better device freely, okay, without any increase of dynamic power consumption. You can use better device. You can use the more powerful processor. So that is the benefit of scaling, and then actually this trend is called the Dennard scaling. Okay, Dennard scaling. So Dennard is the name of the researcher, and then actually he published a paper that explains about the benefits of scaling. Okay, but you know, we just focus on the dynamic power. Okay, so it means if a dynamic power is dominant, and then it means then the power density is the same, and then so also in this equation we do not consider about some other factors like threshold voltage and other factors. Okay, so the Dennard scaling is, if the Dennard scaling continues, then we can use mirror device freely. But the bad thing is that Dennard scaling ended actually some years ago. And the Dennard scaling ended some years ago. It about between 2000 and 2010. So already ended, which means the power density of a processor is increasing by year. And then that's the critical problem of the current processor technology. Okay, actually, the Dennard scaling ended, so which means we cannot develop the performance of the Unicode processor easily. Okay, no, so because power density is a very critical factor of this processor design, the power is tightly coupled with the manufacturing cost, so running cost. And then if the power density increases, which means we cannot use this device easily. Okay, we cannot use. So, okay, then actually I will skip this part because it was actually this slide just explains how CMOS inverter works because the CMOS inverter is some basic circuit that can be built with the post transistor and then post transistor, like PMOS transistor and MOS transistor. So it's a basic. So you know this input voltage. So this is the input signal is connected to the gate of the PMOS and MOS transistor. And then as you can see, you can find the bubble here, which means that this input is inversed for the PMOS transistor. So that's why I explained with the MOS transistor, because the MOS transistor is turned on if this gate voltage is 1, and then it's turned off if this gate voltage is 0, like it's a ground and it's a VDD. And then PMOS is different. So you can find the bubble here, so which means that if it's off for the input voltage is VDD, which means 1, and then it's 0, then it's turned on. So because it's the meaning of the bubble here, so usually in the logic design, bubble means it's the inverse. Okay. So in this case, it's the voltage, the input voltage, input signal changes from 1 to 0. So which means this PMOS transistor is on and the MOS transistor is off. So you know this one node of this PMOS transistor is connected to the VDD, and then another node of this MOS transistor is connected to the ground. You know, and then this node, the node of the PMOS transistor and the NMOS transistor shares the output of this inverter circuit, the output of the circuit. And then, as I explained, so I explained that every circuit has parasitic capacitor. Actually, the voltage level of this circuit is determined by the amount of charge filled in this parasitic capacitor. And it's actually the same to every device, like memory devices or some logic devices. It's the same. It's the data in this digital devices are determined by the voltage level. Also, voltage level influenced by parasitic capacitors. So in this case, it's turned on. So this capacitor is connected to the VDG, which means that, and then if this capacitor has the lower voltage level, then the electric flow, so electric charge flows from VDG to this capacitor. So which means that this parasitic capacitor is filled with the electric charges. It comes the higher voltage. So which means if the input becomes 0, then output becomes 1 and VDD. And then it's the inverse. If input becomes 1, then NMOS transistor turned on and the PMOS transistor is turned off. So actually this node of the parasitic capacitor is connected to the ground. So which means the electric charge is dissipated from this parasitic capacitor. So it means the 0. So how this is how the MOS transistor works in the digital system. Okay, so I explained about the basic operation of the MOS transistors. Actually, this knowledge is used for explaining power consumption of the processors. Okay. So let's take a break for 10 minutes. Let's continue at 11:55. Okay. Okay. So we covered how the CMOS transistor works, and then we also covered the basic operations of the MOS transistors. So actually, the characteristics of this MOS transistor is related to the power consumption of the processor. So I know most of you are not the electrical engineering students. So maybe this topic may be not familiar with you because this is the very low level knowledge in the computer systems. Actually, if you actually in the first class of the architecture course, we learned about some layers in the computer systems, and you know the transistor layer is the very lower layer. But architecture also includes some hardware properties or hardware implementation. So this knowledge is also required. So actually, as I mentioned, the performance and then cost of the processors are tightly related to this semiconductor technology. So it's very important to understand some technology trend and then some very brief, the understanding the brief characteristics of the modern technology, modern semiconductor technology is also important. Okay, so the goal of this study, goal of this research, the process research is actually the two main goals of this process research is performance and cost. And the many are there are many other research topics like the security, reliability, and then some other factors. But the main goals of this process research is the cost, increasing to increase the performance and then reducing cost, like manufacturing cost, running cost. So understanding the semiconductor technology, the actual base technology is very important. Okay. Okay. So I will explain about the power consumption of the processors. And then as I explained, the power consumption of the processor is briefly, we can categorize the power consumption of the processor briefly with the dynamic power and static power. And then this is the equation of the dynamic power. It's a very popular equation. And then with the scaling factor S, then you can see some influences from the CMOS scaling with the scaling factor S. And then as I explained, the C becomes the 1 over S because the size is reduced. And then VDD is also scales 1 over S. And then F scales S. So actually, we can use this table for the clock frequency and then some scaling factors. So P dynamic becomes the 1 over S square. And then the size of the transistor is reduced, then you can include the more transistors in the unit area, it's the same area, the power density is the same. So I already explained about this scaling. So Denard scaling, this is called the Denard scaling. The power density is the same. It's a very good thing. It's not true. But we can also think about some other factors, okay? So in this equation, the Denard scaling, just to mention that, just to assume that we can scale down the C and VDD, also we can scale up F, and then the unit area, the chip area is the same. So power density is the same. The Denard scaling just explains the power density, unit area. But think like this. So if we cannot scale down the VDD, the supply voltage, then what will happen? Actually, VDD is the dynamic power is proportional to the square of VDD square. So actually, the VDD occupies the very large portion of this dynamic power consumption. If the VDD does not scale, so which means that if we cannot scale down the supply voltage, then power density grows. So this is the equation. So when we consider the scaling of in the dynamic power, then we assume that this is the dynamic power of the single transistor. But if it does not reduce this VDD, then what is the power density? Power density becomes the S squared. Okay. So why did I explain this? So, in the previous decades, several decades, the supply voltage of the CPU was about the 5 volt. So 5 volt, and recently, the supply voltage is nearly 1 volt, or sometimes it's slightly lower than the 1 volt, but we can observe that the supply voltage is nearly the same, So actually, with the CMOS scaling, it was easy to reduce the supply voltage, okay? But currently, it's not easy. So benefit of the CMOS scaling is that this channel length is reduced, so we cannot make the better device. But recently, so also the benefit of the CMOS scaling is that we can reduce the supply voltage, but this supply voltage also influenced by some threshold voltage and then some power and then we need to consider some different factors of the power consumption. Then we cannot reduce this supply voltage level more dramatically. So if the supply voltage level is maintained, and then if just the size of the MOS transistor is reduced, and then if the entire chip size is the same, then it will consume the much power, thus S squared. The power consumption is just increased by S squared. Okay, so it also should be considered. And then chip size. So we can use the bigger chips because the Intel Xeon is a server chip. It's the larger area because the Xeon includes the more cores. So and so that's why the server chip is very expensive. So it's related to the manufacturing cost. So the yield. So yield is also very important. The yield is also inversely proportional to I think the yield is inversely proportional to the area 1 over area scale of area, the chip area. Okay. So if the chip size is very large, so then this large chip will also consume much power. And then I also explained that this power is related to the heat, that is thermal. So we need to also consider the thermal issues in the control system. So if the chip consumes more power, then which means that the chip is getting hotter. So we need to also invest more cost to the cooling system or cooling mechanism of this computer system. Also, this power is also related to the packaging. So power is also very critical for the cost of the chip manufacturing. Also, so it's also critical for the running cost of the computer system. So actually, if we just focus on the heat, the thermal, then this thermal dissipation is also related to the running cost of the server system. So actually, power is very critical. So just remember that the power, consumed power by CPU or processor is very, very critical. Then, how can you reduce the dynamic power? If the power is the very critical problems and then critical issues in the control system, then we can reduce it. We need to work hard to reduce the power consumption of the processor. So let's just focus on this dynamic power equation. So if we just see that this dynamic power consumption equation, then how can we reduce the dynamic power? It's simple actually. By the equation, we can reduce this activity factor, so we can use the C, or we can reduce the VDD or F. clock frequency. Okay, there are many factors here. Then let's focus on each factor. Then how can you register this alpha? Alpha is the activity factor. How can you reduce alpha? So actually, if we just see some digital circuit is composed of sequential part and then combinational logic, and another sequential part. So we frequently use the D flip-flop for this sequential part. And then, this sequential part is connected to the clock signal. So it's synchronized by clock signals. So actually, if we just focus on this combination logic, the combination logic is supposed to be the operation of the combination logic is influenced by input data. Right? So there are many inputs here, and then output of this combination logic is determined by combination of input signals. So if the output is changing, so that means that actually there will be many transistors in this combinational logic. And then if some values are changed inside of the combination logic, then which means we run into this example of the CMOS inverter. So the internal value is changed, which means that the power is consumed. So actually, dynamic power means that the power is consumed by changes of these internal values, the combination logic. But think like this, you cannot change this part. So input values, the input of the combination logic is just changed by states of our software and some applications. You cannot change this. It's the software part. The hardware cannot change this part. Then how can we change the activity factor? So actually, we can focus on the clock signal for the sequential logic. So I explained that, we cannot change it. Oops. We cannot change this part. Then only possible part is the clock signals. And how can you change this activity factor of the clock signal? So there are two different techniques. So we can use the power gating, or we can use the clock gating. So actually, these two technologies are widely used in the modern chip design. But I think the power gating is a little bit different, because with the power gating, we just cut off some current from VDD to ground of the circuit. So which means that, the inverter design. So firstly, I will explain about the power gating. So if we just see the inverter like this, oops. So the inverter is working because another node of this PMOS transistor and then a different load of this NMOS transistor is just connected to VDD and ground. So that means the current flows from VDD to ground. So that's why this circuit is working. But if this circuit is not working, that means if this circuit is not used, then we can cut off this power, the path from the power source and the path to the ground. So which means we can just control this connection to the ground, VDD or connection to the ground like this. So we can also add the more transistor here, and then this transistor is controlled by other source. So which means, this most transistor is the electrically controlled switch. So which means that this path from the VDD or path to the ground can be also turned on or turned off by some signals, control signals. And then if we just control this connection to the power source or some connection to the ground, then we can entirely turn on or turn off of this circuit. So this technique is called the power gating. So power source is gated, so controlled by some control signals. But actually, this technique is related to the static power consumption, not dynamic power, because if we just control some power source to the circuit, which means that the entire circuit in this power getting domain is entirely turned off. So which means we cannot use this circuit, we cannot use this domain. So actually, which means that the input signal is not given to this power, this domain, which means that it's turned off by the power gating. So it's not actually related to the dynamic power. The power gating technique is very highly related to the static power consumption actually. Okay. Why? What is the static power? Even though this circuit is not working, the current pass through from VDD to ground. That is the definition of static power. But if we can cut off this path with the power gating, then we can decrease this amount of current from VDD to ground. So that actually this power gating technology is used for decreasing the static power, not dynamic power actually. But you may think that, oh, this is also controlled by most transistors. Then how can you reduce the static power? So, which means static power means that even though the transistor is turned off, the current can do this from between source and drains. So that is the definition of the static power. But also, the power gating is controlled by most transistors. So we can use the different type of transistors for this power gating. So we can also increase the size of the transistor. So we can apply some different threshold the voltage for this transistor for power gating. Okay. So actually, the power gating is related to the static power, not dynamic power. Then clock gating. So clock gating is also widely used in the chip design. So I explained that in the digital circuit, we cannot control the input signals for combinational logic. Okay, we can just control the clock signal. So what is the clock signal? Clock signal is a repeated signal. That is actually the value of the clock signal is changed repeatedly from 1 to 0 or 0 to 1. So it's always active, but the values are changed repeatedly. But this sequential logic can be activated only if the clock edge at some specific clock edge. So which means that if this sequential logic works with the rising edge of the clock, then so we just use the clock operation from 0 to 1. This is the rising edge. But this flip-flop is not always used. So which means that its input signal is not changed. So input signals for this sequential logic is not changed. We don't need to update the clock signal every time, right? So in this case, we can, so let us assume that during this clock cycles, input signals for this flip-flop, like a sequential logic, is not changing. Then we don't need to change clock signal for this period. So we can update the clock signal like this. This is the main idea of the clock gating. So which means if the clock signal is not required, so we just remove the changes in clock signal. So this is the clock gating idea. So with this clock gating, we can reduce the activity factor of this alpha, because I expect we cannot change this part. We can change also this clock signal. Okay, so with this clock gating, we can reduce the dynamic power. And then C is just related to the number of transistors. So cannot reduce. And then VDD. If we can reduce the supply voltage, then the dynamic power is related proportional to the V square. And so if we can reduce the supply voltage, then we can dramatically reduce the dynamic power consumption. Okay, it's the most effective approach. So decreasing this BDD is very critical. And then good thing of the CMOS scaling is that we can reduce the supply voltage, but I explained that correctly. It's not easy. But if we can reduce the supply voltage, it's the best way to reduce the dynamic power consumption. And then also, usually the frequency is proportional to the BDD. So if we can reduce the BDD also, then actually the power. So it's why the P is related to the FQ of the frequency. And so if we can reduce the frequency also, then we can reduce the dynamic power consumption dramatically. Okay, but we can for reducing the supply voltage and then clock frequency, then we need to sacrifice the performance of the processor. Okay? So, the DVFS, dynamic voltage and frequency scaling techniques are widely used in the commodity processors like Intel or AMD and some other processors. That's why, so in order to reduce the dynamic power, then we need to adjust the voltage level. Also, we need to adjust the frequency levels. So, based on the required performance level, the voltage, supply voltage, and the frequency and the working frequency is dynamically changed. This technique is called the DVFS. So if we can adjust this supply voltage and the frequency intelligently, then we can reduce the power consumption, dynamic power consumption. So DVFS is some very widely used technique to reduce dynamic power consumption, but intelligently. It depends on the demands to processors. Okay. And then other scaling approaches. So actually, we need to focus on the threshold voltage also. Why threshold voltage is important? Why is critical? Because the threshold voltage determines the speed speed of a circuit also VTH, the threshold voltage, also decides the amount of static power. We'll also cover the static power later. But if you see this current level, like the current IDS is the proportional to the beta multiplied VDD minus VTH. What does that mean? If the IDS, if we can increase the IDS, so I explained that. So parasitic capacitors can be quickly filled with the electric charge. So that's why increasing IDS is good for increasing performance of a circuit. So how can we increase this actually IDS? So we can increase the VDD, but it's not a good solution because if we increase the VDD, then this processor will consume more dynamic power. So another possible solution is that we can adjust the threshold voltage here. So if we can reduce the threshold voltage, then we can make faster circuit, faster device. But it's not a good solution for static power. So I will also discuss about the static power. But if we just see this static power equation, we can find the threshold voltage here. So actually, the bad thing about the static power is that the static power consumption is exponential to the threshold voltage. So which means that if we reduce the threshold voltage of our CMOS circuit, then static power increase exponentially. Oh, that's so bad, actually. So that's some dilemma of the current semiconductor technology. So the good thing of the CMOS scaling is that we can reduce the VDD. So and then in order to reduce the supply voltage, then we need to also reduce the threshold voltage. But the bad thing of reducing threshold voltage means that the static power increases exponentially. Then recently the static power occupies almost half, 40 to 50% of the total power consumption. It's a very critical problem. So if we cannot reduce the threshold voltage, then which means we cannot reduce the supply voltage. So that means the benefits by CMOS scaling is nullified. So actually, this new chip will consume more power, more dynamic power. So just remember that by adjusting this threshold voltage, we can make a faster device or we can make slow device. Okay, but we can also we can also observe the disadvantage of reducing the threshold voltage system, the static power. Okay. Then, how can you apply this property? How can you apply this property? A CMOS device can have multiple threshold voltage level. So this is called the empty CMOS. So which means, actually this is also the static power solution. So why do we need very low threshold voltage level because our circuit need to work very quickly, so fast. So which means high performance. So in order to achieve higher performance, then we need to reduce the threshold voltage. But this device, if we reduce the threshold voltage, and then the static power will increase exponentially, which means this device will consume much more power. So this is very critical problem. But if we just categorize our circuits, the many parts, and some parts need to work very fast. But for some part, so we can run some part with very slowly. So which means some part is critical. Like we need higher performance for some components, but some components we don't need the high performance for some other components. So what is the idea? We can apply different threshold voltage level for the different components. So for the high performance is required, we can reduce the threshold voltage, but if a circuit can work very slowly, then we can increase the supply, threshold voltage. Threshold voltage. This technique is called the anti-CMOS. We can apply the different level of the threshold voltage. So, which means the entire processor chip may have different domains regarding the voltage, supply voltage, working frequency, and threshold voltage level. Okay, based on the demanded performance. So this is some techniques to reduce the power consumption in the modern CPU processors. Okay, then let's think about the power consumption by parallelism. So this is the some unique. So I said that we can think like the the typical digital circuit looks like this. Is a combination logic, and then between the input and output of the combination logic, we can find the sequential logic, like a flip-flop. And then this is the some base digital circuit design, and then with some parallelism, so we can apply the pipelining to exploit the instruction level parallelism. Also, we can apply the parallel processing. Which means that we can invest the more combination logic, more resources, and then so we can also increase the area. But with the more resources, then we can increase the throughput of our circuit. So, and also that this is the this combinational logic have delays of 16F04. So this is just represent the delay of this circuit. It's the combinational logic. So with the 16F04, then this combinational logic has the delay of the 16, like here. And then with the pipelining, then we can divide this combinational logic to the two parts. Okay. So what is the benefit of this pipeline? But in order to achieve the same performance, the clock frequency is the same. It's the same. In order to achieve the same performance, then what is the benefit? If we apply the pipelining and then the clock frequency is the same. So combinational logic is split into two parts. So the same. So half of the delay, which have the half of the delays, like 8F44 and then 8F44. And then the clock frequency is the same. What's the benefit? So what's the advantage of this circuit? So with the pipelining, if the clock frequency is the same, then we can reduce the supply voltage. Okay, so what is the benefit? If the VDD becomes the 1 over VDD, so the origin people, so we can reduce the supply voltage level with the half of the original voltage level. So what is the dynamic power? And dynamic power becomes the quarter of original dynamic power. So that is the benefit of the pipeline. So also, let's think about the parallel processing. So in order to achieve the same performance, it's a very simplified view, but you need to remember that this is a very simplified view. We can already know that if we just use the more pipeline stages, then the increased performance is not proportional to the number of pipeline stages because of the hazard. But it's a very simplified view. But if we apply the parallel processing, what is the benefit? So this is actually the combinational logic has the same delay, and then we invest the more combinational logic, 2x. Then in order to achieve the same performance, then we can reduce the clock frequency by half, 1 over f. So what is the benefit? If we just focus on the dynamic power, alpha C V square F, actually this circuit occupies the twice of this area. So C becomes the 2, and then F becomes the 1 over 2. And how about the voltage? If we can, reduce this frequency level by half, then we can also reduce the supply voltage level by half. So the power consumption becomes the 1 over 4 of original power consumption. So that is also the benefit of the parallelism. So what can you say? So we can say that we can apply some different approaches like pipelining or then parallel processing. And if we just focus on the dynamic power consumption with the most stage like pipelining and then with some parallel processing, then the power consumption can be decreased. But so we can apply some different design approach to achieve the lower power consumption or lower dynamic power consumption. And then let's focus on the static power. So I mentioned that the static power is getting more critical, more and more critical recently, and so we need to also know about some impact from static power. So this is the static power equation, like VDD and then IDS 0. So actually, the definition of the static power means that actually the static power is not defined in the three regions of the CMOS operation, most transistor operation, because the static power actually static power is related to this region, cut-off region. Okay, because the definition of the static power means that even though the most transistor is turned off, that means that it's a cut-off region. The current flows from between source and drain. That is the definition of static power. So it works in the cut-off region. And then this is the equation of the static power. And if you can see, the static power is related to the proportional to the supply voltage. And it's obvious because it's, even though the most transistor is turned off, we can observe some resistance. And then through this resistance, the current flows from VDD to ground. Okay, and then the power equation is the VI. So it's also related to the current level. But actually, this is VS0 is the some parameter. And then also we need to focus on this threshold voltage. So this is some parameters defined by Dt, and then this is a constant, the beta is also constant. So, and then this Bt is the function of the temperature, the working temperature. So Bt is inversely proportional to the temperature. So it's also influenced by the working temperature. So it is why. So it is also important, but we need to focus on this part. If the same working temperature, so this static power is influenced by threshold voltage. Okay, the idea is some constant parameter. If this T is the same, temperature is the same. So this static power is proportional to the supply voltage and threshold voltage. Okay. So problem is that this static power is exponentially proportional to the inversely proportional to the threshold voltage level. So I already explained. So not to reduce this static power, we need to set the higher threshold voltage. Okay. So I already explained about this power gating technology here. Actually, the power gating is used for reducing static power because it just cut this path from VDD to ground with the power gating. Okay, so this technology also can be used. And then another technology is this adjusting threshold voltage. Okay, so if we set the threshold voltage more higher, then we can also reduce the static power. And then, but if we cannot adjust we cannot apply this technique, then static power is proportional to the chip area. So that is the number of transistors actually. That's obvious actually. So what is the static power? Even though the transistors are turned off, the current flows through the transistors and then the power is consumed. Which means if there are many transistors, then these transistors will consume more static power. So static power is proportional to the area. Okay. So if we just consider the static power, the multi-core is not a good idea because with the multi-core, then with the multi-core we can increase the performance and the throughput of a processor. But if we apply the multi-core architecture, then area is also increased. Which means that even if the area is increased, then the static power consumption is also increases. So that's the problem. So actually, so in this example, we just consider the dynamic power. So we can also reduce the dynamic power with the pipelining and the parallel processing. And then, in these both scenarios, we can observe that the dynamic power becomes the core of the original dynamic power, like P, and P divided by 4. But we did not consider the static power. Now, which one is better, actually, if we consider the static power? This one or this one? So static power is proportional to the area. So which one has larger area? So actually, this one has 2x area, right? So even though the dynamic power reduction is the same, if we just consider the static power, this approach is not good because it will consume 2x of static power. Okay, the area is increased because the combinational logic is just occupies 2x area, but with the pipelining, we just split this combinational logic, and then so the area is nearly the same. But it's also true that we need to add some more sequential logic here, but if we just consider the area of the combinational logic. Okay. But we already know that because of power consumption, so we are using the multi-core architecture, chip multiprocessor. So actually, we can apply some different some techniques or different approaches like DPFS, and then the same unicore performance. Right? So actually, we need to consider some different spectrum of the dynamic power or static power consumption in this case. Okay, so I explained about the static power and the dynamic power consumption, and it is very critical for the process design. Okay, so try to understand about this static power and dynamic power consumption. So actually, if you include some new ideas on your process of design, then you need to also consider about the cost. Okay, so actually, the main purpose of the new idea is to increase the performance first. Then, but we need to also consider the cost of this idea. Okay, which means in your paper, in your architecture paper, you need to also include some estimated result of power consumption and energy consumption. Okay, because this is the cost. Okay, then we can apply some different metrics for measuring and comparing some cost of the system. Okay, so first we can consider the power consumption because the power consumption is related to the manufacturing cost, also the running cost. So, but if we just the power consumption is primarily related to the thermal. That means that heat dissipation in the processor. Okay, so actually the power is related to the packaging cost or cooling cost of a system. And then actually if we just focused on the some running cost of our system, then we need to focus on the energy. Okay, so what is the energy? Energy is the power multiplied by execution time, the delta T actually. So think like this. If we reduce the power consumption by half, 1 over P, but if the performance of this processor is becomes the half of the original performance, then the execution time becomes the twice of the original execution time. Okay. Then the energy consumption. What is the energy consumption? The energy consumption is actually the same PE in the original system. So the benefit is if we can reduce the power consumption, so it's beneficial. So which means that we can reduce the cooling cost, or we can reduce also we can use some cheaper packaging for our chip. But if we just consider some running cost like energy, then energy consumption is the same because the performance is also reduced by half. So, and then energy is also critical for the mobile devices because mobile device has the limited power source, the battery. So in this case, so for the mobile device, we need to also focus on the energy consumption. Okay, so energy is the power multiplied by delay. Okay. Then sometimes we can use some different method like energy multiplied by delay. Okay. So which means it's actually P multiplied D squared. So what does that mean? So if we just focus more on the performance of the system, then we can use the energy multiplied by delay method. Okay, so we can just focus on the performance, higher weight to the performance. Also, we can use the ED square. Okay, so like this, which means that we can just focus more performance. So, for example, mobile, in order to compare some cost of the power and then some cost, then we can use this energy. So actually, the mobile device can use the energy for the cost of our system. But if we just compare the cost of the server system, for the server system, performance is important. Okay, then we can use the ED or ED square. Okay, it means based on the different properties of the system, then we can apply the different performance and the different metrics, cost metrics. Okay, so sometimes you can use the ED or sometimes with the ED square in our system. Okay, so I will stop here. Any questions? 잘 안 들리는데 좀 크게. 네. 네, 그러니까는 사실 이제 파워 게이팅은 여기 설명을 내가 이제 설명을 했지만 보통 이제 디지털 서킷에서 이제 알파를 줄이기 위해서는 클락을 줄일 수밖에 없거든요. 그러니까 사실 여기 파워 게이팅 하면은 전체적인 서킷을 끄는 거기 때문에 클락도 이제 글로 안 들어갈 거잖아요. 그러니까 사실 뭐 다이나믹 파워도 줄일 수는 있긴 해요. 근데 더 이제 그 실제적인 목적으로는 결국에는 파워 소스랑 그라운드까지 이어지는 그 서킷 그 패스를 끊는 거기 때문에 더 스태틱 파워를 더 줄이기 위해서 더 이제 쓰이는 기술이라고 이제 좀 우리가 생각할 수가 있어요. 물론 이제 그쪽으로 가는 이제 클락 시그널까지 딱 꺼지니까는 뭐 다이나믹 파워 줄일 수 있는 것도 맞긴 한데, 액티비티 팩터를 줄여서 뭐 그렇지만 이제 그 메인 퍼포즈는 스태틱 파워를 줄이기 위한 거다. 그래 뭐 그러면 뭐 사실 단순하잖아요. 전체적으로 이 컴포넌트를 그냥 꺼버리는 거기 때문에 전체적으로 이제 그 커런트가 흐르는 걸 막는 거고 스태틱 커런트가 흐르는 걸 막는 거고. 그래서 이제 스태틱 파워 줄이기 위한 기법으로 많이 쓴다. 생각하면 되겠습니다. 이런 거 같은 경우에는 EDA, 그러니까는 뭐 대기나 이제 데이트 같은 데가 EDA 컨퍼런스인데 그런 그 EDA 쪽 연구에서 이제 많이 쓰이고 또 많이 이제 그 트랜지스터 모델 만들어 가지고 이제 시뮬레이션해서 얼마나 이제 우리가 이득을 얻을 수 있을까 이런 쪽으로 이제 많이 쓰이는 기술이긴 해요. 물론 이제 한때 이제 2010년 2010년대 초반 중반까지는 이제 다크 실리콘이라고 해가지고 프로세서에 여러 이제 컴포넌트들 아니면 코어 같은 경우에도 얘네들을 켜고 끄고 해가지고 우리가 이제 그런 스테릭 파워, 리키지 파워를 이제 줄이고 그거를 통해서 어떻게 이제 프로세서의 성능을 유지를 하면서 파워 컨섬션을 이제 줄일 수 있을까 그런 것들이 많이 화두가 되었었어요. 그래서 뭐 다크 실리콘 이라고 해가지고 우리가 이제 코어를 이제 크게 만들고 트랜지스터를 많이 그 칩에다 이제 넣어가지고 이제 돌리긴 하지만은 실제적으로 펴져 있는 부분들은 적을 수도 있다. 뭐 이런 식으로 해가지고 다크 실리콘에 대해서도 많이 연구를 하고 있었는데 요새는 그런 트렌드들이 그렇게 이제 기술이 또 이제 세츄레이션 됐는지 트렌드가 다크 실리콘 얘기는 또 잘 안 나오더라고요. 그래서 그런 차이가 있긴 한데 어쨌든 얘는 이제 스태틱 파워를 줄이기 위한 기법으로 많이 쓰고 있습니다. 네, 질문 없으면 됐으면은 네. Thank you for your attention and see you in the next class. 네, 그리고 이제 파워 에너지는 항상 중요한 문제이기 때문에 퍼포먼스와 더불어 항상 이제 잘 알고 있고 또 여기 될 아이디어도 그 지식도 이제 베이스로 항상 생각하고 있으면 좋습니다. See you in the next class.
감사합니다.
Bye guys.